everyone. So today we're moving into some lessons on graphing with variation functions. And today specifically we're focusing mostly just on direct variation, although there's two types of direct variation. There's the simple direct variation, and then there's direct variation where we start throwing exponents in. So this video will be split kind of into two parts, and those will be our two parts. So this first video is focusing just on simple direct variation. And we're going to talk about what these graphs look like and some of the properties. And really, I think the big thing to walk away from this with today is not so much how do you plot points and physically make graphs, but just in general, what do these graphs look like? What does the k value do to the graph? And what are the different properties that you need to know about all of the variation function graphs. So we're going to get started here. This is in your notes packet, and we're going to do one example where we actually do plot it point by point, but then from there on out we kind of want to talk more in general. Okay, so let me get rid of my face. There we go. Okay, so let's say I give you the function y equals 3x. So what I'm really saying is that for every x value I choose, my y value is going to be 3 times bigger. So if I were to choose, let's say 1, my y value would be 3. If I was to choose 2, my y value would be 6. If I was to choose -5, my y value would be oops, I'm writing as I talk. My y value would be -15. What if I were to choose 0? Well, 3 times 0 is just 0, so it would still just be 0. Okay? So if I were to graph these points, and this is just a selection of points. I could have kept going all day and done a ton of points, but I think you get the pattern here. So if I go to x is 1 and y is 3, that's this right here. X is 2 and y is 6. By the way, on yours, I don't remember if you have an actual grid drawn in here or not. Again, as long as you get the approximate shape, you're really okay. I can go to -5, but I'm not sure this goes all the way down to -15. 9, 10, looks like it goes to 12. So -15 is going to be, I don't know, somewhere way down here. And then, of course, 0, 0. And what I really want you to see here is that the shape that this graph makes is a nice straight line. And I'm going to, let's see, -1 would go with -3. I'm going to throw a few more points in here just to help my line be a little bit straighter. Okay. But that's what this function would look like. Okay. And you've learned about linear functions before, or at least I'm pretty sure you have. Probably in 8th grade, you probably did a section on linear functions. If you remember back to mx plus b, that's kind of going to be where we're heading with this. So I'm actually going to skip this little piece for a second because I want to talk about these words down here. So if you do need a second to pause and copy down these definitions, please feel free to do so. But with any type of graph, we talk about something called the average rate of change. An average rate of change is just a comparison to really dependent variable, that's your y. So it's a comparison of how fast is the y changing compared to how fast the x is changing. Or how fast am I growing up and down compared to how far I'm traveling left and right. So in general, that's called rate of change. Okay, and we're going to get more into rate of change in a little while. Now, if I was to do rate of change on this particular graph, I would pick any 2 points that I want. So let's say this point and this point, any 2. And I would say, well, in that distance, I went up by 6. Okay, so I increased by 6 over a distance of 2 units on the x-axis. So my rate of change would be 6 over 2, which is just 3. And if I did that for another set of points on the same graph, so let's say I went from here all the way up to here. I should have used a different color here, but let's suppose I did that. Let's see, this is at -6, so that means I went up 6 plus 3 more. So grand total here, I went up a distance of 9 compared to a horizontal distance of 3. So looking at those 2 points, my rate of change would be 9/3, which is still just 3. Now this right here is sort of unusual. Usually on a graph, when we do rate of change, it's not always necessarily the same. Okay, it depends on which 2 points we picked. But this particular type of graph, this linear graph that we're looking at, that's one of its properties, is that the rate of change is always constant. Okay, so we may want to just jot that down someplace here, that rate of change is constant in linear functions, any linear function. And because it's constant, it gets its own special name. And its special name is the slope. And maybe as I was doing that calculation a second ago, some of you were going, well, hey, I've done that before. You probably have. So to find slope of a line, you're really just finding rate of change. And since you're already familiar with slope, maybe it's easier to think about it as rate of change is found the same way that you would find slope. The difference is going to be is when we move away from straight lines on our graphs, when we move to some more interesting graphs, the rate of change is not always going to be constant. But it is in linear functions, which means I can pick any pair of points to do rate of change, and I still find the same thing. Okay? So slope is just rate of change on a linear graph. Okay? We only really talk about slope when we're talking about linear graphs. So now let's go back up here to this sentence that I didn't fill in. The graph of y equals k to the x is always linear, or it always makes a straight line. Okay? And the slope, and we didn't really talk about this number 3 here, okay? But the fact that I got 3 should ring a bell because the function that I was using was y equals 3x. So your slope is always just the k value. Okay, so when I give you a function and I say here graph this, the slope can be determined if you know what the k value is. Okay, I know that all sounds a little bit confusing. Once we get into some of the more specific properties, I think you'll be okay. The one thing that I should point out here, and I wish I had left a little more space in here, but maybe we'll just carve out some space over here, is that when k is positive, your graph is going to slope up to the right. And when k is negative, your graph slopes down to the right. So the value of that k value does make a big difference. And then the numerical value of k makes a difference too, but we're going to get more into that, I think, later on. Okay, so you don't have to worry so much about what does that number 3 do to my graph, but I do want you to know the difference between positive and negative and which way the line should be pointing. Okay, so let's talk about just some general properties. In general, if we're working with a linear function, I like that I have these 2 pictures right here. A linear function covers everything from left to right on our graph. So every single one of these linear functions has a domain of all real numbers. And it also covers everywhere going up and down on a graph. So our range is all real numbers. Now, when we're working with these direct variation graphs, do you remember that I threw this 0, 0 in here? Okay. That point is going to show up on every single one of these functions because no matter what I put in for k, I could do y equals 2x, I could do y equals 10x, I could do y equals 500x. No matter what I put in for k, when I plug in a 0 for x, I'm going to get a 0 out for y. And so every single one of these functions contains the point 0, 0. So the y-intercept is at the origin, and I'm just going to make a note here that these graphs always contain 0, 0. Okay? So any one of these direct variation graphs contains 0, 0. Now, some of you might be thinking, well, I know I've seen lines before that don't cross through 0, 0. That's true, but in order to make it not cross through 0, 0, we have to throw some addition and subtraction in there. So like 3x plus 1, for example. That's not going to cross through 0, 0. That one's going to have a y-intercept of 1. But this is not technically direct variation because it's got addition and subtraction in there. only this is direct variation. So you can kind of ignore that. I just kind of want to make a point there. And then this might be the only concept that you're really kind of new with. I don't think you've seen this before, is the limit. So I'm going to start with just the k is positive function. And that's going to go straight to the origin like this. And so what I'm asking is, as x approaches infinity, what happens to your y values? Okay, so I'm asking, if I walk out along this x-axis, and I keep walking forever and ever and ever and ever, what's happening to the y values on my graph? Well, on this particular one, those y values are going up and up and up forever. Okay? And so as x approaches infinity, gosh, that's a terrible infinity sign. But my y is going up and up and up forever, so I'm going to say y approaches infinity. And then same thing going backwards. If x approaches negative infinity, that's how we should say this. So that would be walking along this way towards negative infinity. Negative infinity would be in this direction. As we head out towards negative infinity, what's happening to my y values? Well, they're going down and down and down forever. Okay, and so going down forever, we would say is negative infinity. Okay, now these are specific to when k is positive. Something a little different is going to happen when k is negative. I'm just going to, for the sake of what we're doing here, I'm just going to do this. So I'm going to cover this up and draw myself a new graph, but this time I'm going to make the k value be negative. So I'm going to make the graph go this way. Pretend that goes through the origin. So when k is negative and x approaches infinity, so as I walk out along the x-axis forever and ever and ever in this direction towards infinity, what's happening to my y values? They're going down and down and down forever. Okay? And so if they're going down forever, we would say y approaches negative infinity. And then, as x approaches negative infinity, so as we walk forever and ever this way, what's happening to our y values? Well, they're going up and up and up forever. So we would say as x approaches negative infinity, y approaches regular infinity, positive infinity, because it's going upward forever. So that's when k is negative. So basically making k negative makes these two things flip-flop. But I'll be honest, I would not try to memorize this because look at how confusing that little chart looks. Okay? I would not try to memorize. In fact, I would think about where did these come from? When I say x goes to infinity, can you follow a graph and think about, as I walk forever in this direction, what's happening to my graph? Well, it's heading down forever. Okay? And so that's negative infinity. And so you're much better off just kind of visualizing it every time than you are trying to memorize it. Okay, that's really it for this first little piece. Next up, we're going to be talking about direct square functions.